Hello, welcome to Recitation 3. Today, our learning objectives are going to be the following. So we're going to calculate a 5-number summary of a small data set. So we're going to calculate minimum, lower quartile, median, upper quartile, and maximum. We have to calculate the low and extreme outliers of a small data set, and we want to be able to determine whether a described set of data is symmetric, right skewed, or left skewed. So task 1, here are annual numbers of deaths from tornadoes in the United States of America from 1990 through 2000. So here we have a list of numbers. And so we want to find the following statistics. So we'll want to find the lower quartile, the upper quartile, the interquartile range, the lower fence, which is calculated with the quartile minus 1.5 times the interquartile range, and then the upper fence, which is equal to the quartile 3 plus 1.5 times the interquartile range, and then to calculate the range. So here I kind of worked out each part of the task. So the first thing that I did, so we were given a list of numbers, and it's a total of 11 numbers. So here our sample size is 11. And I wanted to sort them from smallest to largest. So that's what I did here. And it's also, and I also sorted them from smallest to largest here when I actually started looking at the different statistics. So first we want to calculate or find the lower quartile, which is the 25th percentile of the data set. So after I sort them from smallest to largest, I then work my way to see what that middle value is. So I cross off on my paper, like each outer value. So the maximum, the minimum, and then I keep working my way, crossing off or using my finger to get to the center, which that center value is 40. And so that's the median, or the second quartile. And then here we have, so below the median is the lower half of our data set, and here we have the upper half of our data set. And so the lower quartile, how I like to think of it, is kind of like the median of the lower half of the data set, and the upper quartile is kind of the median of the upper half. So once I found the median and then found the lower half of the data and the upper half of the data, I kind of started by crossing off the largest value of the lower half and then the smallest value, and so on and so forth. So that center value here is 33. So that is going to be quartile 1, or the lower quartile. And then so that answers A, which is 33. And then the upper quartile, which is the 75th percentile of the data, is going to be 69. So you do the same thing where after you find the median and you have the upper half, then I crossed off the smallest, which would be 53, and then the largest, 130, and I kind of work my way into the center, which is 69. So that's the upper quartile, Q3. And then we want to calculate the interquartile range. And so that's calculated by taking quartile 3 and subtracting quartile 1 from that. So our quartile 3, or the upper quartile, is 69. And then we'll subtract our lower quartile, which is 33. So 69 minus 33 is 36. Then we want to calculate the lower fence. So the lower fence is calculated by taking the lower quartile and then subtracting 1.5 times the interquartile range. So in C, the interquartile range is 36. So when you do 33 minus 1.5 times 36, you get negative 21. That's the lower fence. And then the upper fence, you're going to take, instead of quartile 1 this time, you're going to take the upper quartile, quartile 3, and then we're going to add 1.5 times the interquartile range. And so the interquartile range, like we said, was 36. And this time our upper quartile is 69. So when you do 69 plus 1.5 times 36, you get 123. And then the range is the maximum minus the minimum value. So here the maximum value is 130. The minimum value is 25. So when you do that subtraction, you get 105. So that is the range. And those answers match the key here. On to task 2. So scores on a mathematics assessment test for 8th graders have a mean of 282, a 10th percentile of 231, a 25th percentile of 251, a 75th percentile of 304, and a 90th percentile of 323. Which of the following statements of the numerical descriptive measures is or are correct? So whenever I'm given any task, I always like writing out the information that I'm given first, just so that way as I go on in the course and we're given more information and the problems get more involved, or we're given more information, I can kind of keep track of everything. So we were given what the mean was, what the 10th percentile, 25th percentile, 75th percentile, and 90th percentile was. And so here I want to just see visually what it looks like, and then I'll go back and see if the statements are correct. So here the 10th percentile is 231. And well, let's first look at what that first statement is. So a 10th percentile of 231 means that 10% of the scores fall below 231 and 90% of the scores fall above 231. So here I'm drawing a somewhat of a symmetrical normal curve, because usually that's kind of how I visualize it. And I'm just assuming that here for an assessment for 8th graders, it follows some sort of shape, but it's okay if the shape's not necessarily drawn to scale or whatever. I just use this to kind of visualize. So here, if the 10th percentile is 231, I'm first going to draw that, okay, let's say 231 is here and it's the 10th percentile. That would mean that 10% of the data, or 10% of the scores, are to the left of that value or less than 231. And then 90% of the scores are to the right of that value or greater than 231. And so if I look here, that's essentially what A is saying, where 10% of the scores fall below 231 and 90% of the scores fall above 231. So A is correct. So next, B. So what does a 25th percentile equal to 251 mean? So if I were to draw this out, I'm going to plot where 251 is, and I know it's the 25th percentile. So that means 25% of the scores fall below 251, and then 75% fall above. And you always want to make sure that the area under the curve, the percentages will equal to 100%, right? Because then you'll get everyone. So how I figure out this value, if it's not memorized, you can always do 100% minus 25% is 75%, and same here for part A, because you want to get 100% of the scores like under the curve. So anyways, so going back to B, it states that a 25 percentile of 251 means that 25% of the scores fall below 251. That's correct. And 75% of the scores fall above 251. That's also correct. So now on to C. What does a 75th percentile of 304 mean? So, oops, sorry. Okay, so here I'm going to draw 300. 304 is the 75th percentile. So that means here I'm going to first start with writing the score down, and then 75% of the scores fall below 304, and then here is the remaining 25% of the scores, which are above 304, and that is what C says, where 75% of the scores fall below, and then 25% of the scores fall above. So that's correct. And then lastly is D, a 90th percentile of 323. So here, I'm going to plot 323. And so that means 90% of the scores are going to be below 323 or less than 323. And then 10% of the scores are going to be greater than 323. So 90% plus 10% is 100%. So that checks out. So if I look at what's written, we have 90% of the scores fall below 323 and 10% of the scores fall above 323. So all of these statements are correct. And on to task 3. So a sample data set has a mean of 61 and a standard deviation of 10. Determine which of the following sample measurements are outliers. Okay, so here's a hint. We're going to use the absolute values of z-scores to determine which of the sample measurements are outliers. And so we're interested in, here we have x equal to 95, 51, 63, and 70. So here I wrote out the information that we had. We were given that the sample mean is 61, which is, the mean is also x bar. The standard deviation of the sample is 10. And so if we're using a z-score, the way we kind of figure out if we have an outlier is if the absolute value of the z-score is greater than 2, then we have a possible outlier. If the absolute value of the z-score is greater than 3, then we have like an outlier, an extreme outlier. So the first number we were given is 95. So let's calculate the z-score for 95. So a sample z-score is calculated by taking our value, which I'm referring to x. So these values earlier, I said x. If that was confusing, I'm referring to this x here is our value that we're interested in. So for each of these values here, 95, 51, 63, and 70, each time we calculate their z-scores, that individual number is going to be put here. And then we have our x bar, which is our mean, which we were given as 61. And then we have the sample standard deviation, which is S, which we were given as 10. So now it's essentially a plug and chug where we have all of these values and we're going to calculate our z-scores. And then once we calculate the z-score, we're going to take that absolute value and see if that absolute value is greater than 3 to determine whether it's an outlier. So first, we want to see if 95 is an outlier. So we're going to calculate the z-score for 95. So that's going to be 95 minus the mean, which is 61, divided by 10. So 95 minus 61 is 34, and that divided by 10 is 3.4. So if we take the absolute value of 3.4, that's going to be positive 3.4, and that's greater than 3. So that means that 95 is an outlier in this sample data set. And that aligns with the correct answer. So now B is 51. So let's calculate that z-score. So 51 minus x bar, which is the mean, 61 divided by this sample standard deviation, which is 10. So 51 minus 61 is negative 10, divided by 10 is negative 1. So but we want to take the absolute value and see if that's greater than 3. So the absolute value of -1 is +1, and that's not greater than 3. So we do not have an outlier. So 51 is not an outlier. Next, we want to calculate the z-score for 63. So 63 minus the mean, which is 61, divided by 10, which is the standard deviation, is going to be 2 divided by 10, which is 0.2. And then you take the absolute value, which it was already positive. So anyways, that's positive 0.2. And then that's not greater than 3. So we do not have an outlier. So 63 is not an outlier. Next, we want to calculate the z-score for 70. So 70 minus the mean, 61 divided by 10, is 9/10 or 0.9. And so the absolute value of 0.9 is positive 0.9 still. So that is not greater than 3. So we do not have an outlier. So the only outlier that we had was 95 for this data set. Task 4 is very similar. We're going to be using z-scores again, and we're given the mean and the standard deviation, but now the mean is 57 and the standard deviation is 11. And then we're given these values. So 65, 21, 72, and 98. So on to task 4. I'm writing down what's given in the problem, just so I can keep things straight. And I recommend that you do that too. And so let's see. So the z-score for 65. So 65 minus the mean, which now is 57, divided by the standard deviation, which is 11, is going to give us 0.7272 repeating. So, and the absolute value of that is 0.7272, and that's not greater than 3, so we do not have an outlier. So 65 is not an outlier. Next, let's calculate the z-score for 21. So 21 minus the mean, which is 57, is 36, and then we're dividing that by the standard deviation, which is 11, and so we get negative 3.2727, and so the absolute value of negative 3.2727 is positive 3.2727, and that's greater than 3, so we have an outlier for 21 is an outlier. Next is 72. So 72 minus the mean, which is 57, divided by 11, we get 1.3636. And that is the absolute value of that is not greater than 3. So we do not have an outlier. And then the z-score for 98, we're going to subtract the mean, which is 57, divide that by 11, and we get 3.7272 repeating, and that absolute value is positive, and that is greater than 3. And so we have an outlier or an extreme outlier. And the reason why, let's see, where did I put it? So here you can think of it as an extreme outlier if it's greater than 3. If it's greater than 2, then we have a possible outlier. Okay. So here that aligned with what we just discussed. So A is not an outlier, B is an extreme outlier, C is not an outlier, and D is an extreme outlier. Task 5. Would you expect the data sets described below to possess relative frequency distributions that are symmetric, skewed to the right, or skewed to the left? Explain. So here we have our different scenarios, and we want to know, okay, would, for example, the salaries of all persons employed by a large university be skewed to the left, be skewed to the right, or be symmetric? So I always try to visualize what it would look like. So here, I would assume that it would be skewed to the right, because you're going to have most of the people at the large university make well, you have the students that like make, I don't know how much students make, maybe like minimum wage or something, or maybe a little over minimum wage, but most of the people make like a smaller amount of money. And then when you get to like the highest positions where people are making a lot of money, you have very few people as people make more money. So here you can think of, this is like, if I should have wrote under here, like this would be like 0 would be way over here, like you make no money and then you'd make a lot of money or something. So for example, if you think, the dean would make more money than the people who are, I don't know, answering phones for the what do you call, the registrar's office. So or those types of positions. So the positions of higher positions are more few. So it's skewed to the right, it's spread to the right. All right, so B, grades on an easy test. So on an easy test, you would expect that more people would score high, right? We would have more high scores than low scores. So here it would be skewed to the left, because the spread, it gets more spread out on the left. There's fewer low scores than there are high scores for an easy test. So then grades on a difficult test are going to be the opposite, where you'll have more students that score, you have lower scores because it's difficult, and then you'll have a few students that still score really high. So that's going to be skewed to the right. D is the amounts of time students in your class studied last week. So assuming that you all are dedicated students and that we have majority of people, well, actually, let's say, I guess the professor assumed the opposite, where maybe people weren't studying as much because they were watching football or going and being social or whatever and have other obligations. And maybe it's the beginning of the semester, so people are studying less than they will later on. So we have people studying for less, more people are studying maybe, I don't know, a half hour to, I don't know, a few hours every week. A lot of people are majority are studying maybe like 3 to 5 hours, and then you have maybe a few students that are studying, I don't know, 15 hours or something. And I'm just making up these numbers, so don't necessarily feel bad if I said a number of hours studied and you work that or not. But anyways, okay, so here we would have it be skewed to the right. And then E, ages of automobiles on a used car lot. So here I would assume that it's somewhat symmetric because there's probably majority of automobiles that are very similar in age to each other, and then we've got a few older automobiles and then a few younger automobiles, or and by older and younger I mean how like how old the car is, how many years the car is. So I would assume somewhat symmetric. And then F, the amounts of time spent by student on a difficult examination where the maximum time is 50 minutes. So here the amount of time, so I would assume that if it's a difficult examination, then everyone's probably going to be spending most of the time offered. So we would have the data would be skewed to the left because majority of people are here at the larger values, but then you'd still have those few students that maybe can get it done in a half hour or 20 minutes or 10 minutes. Well, maybe there's someone that can get an exam done in 10 minutes, but really majority of people are going to be using the full 50 minutes. So that's skewed to the left. Okay. Those are the answers. We just walked through. Okay, task 6. A sample of 20 glass bottles of a particular type was selected, and the internal pressure strength of each bottle was determined. Consider the following partial sample information. So here we have the median is 202.2. The lower quartile or lower fourth is 196. The upper fourth, Q3, is 216.8. And then we have the 3 smallest observations and the 3 largest observations. And we want to be able to determine which observations are low outliers or mild outliers and which are high outliers or extreme outliers. Okay, so here I'm just going to write down first the information that we have. So we were given our sample size of 20 glass bottles, and then we have the information for the median, the lower quartile, the upper quartile, and then the 3 smallest observations, the 3 largest observations. So unlike before, we were able to use z-scores to determine whether a data point was an outlier. But we're not, this time we can't really use z-scores because of the information we're given, because in this information we weren't given the mean and we weren't given the sample standard deviation. But you can still determine outliers by using box plots. And so that's what we're going to do here. So I know this looks a little overwhelming, but I'm going to try to break it down. So there's ways to detect whether we have a mild outliers or suspect outliers, or if we have highly suspect outliers or extreme outliers. So here, low mild outliers, I think of like lowly suspect outliers, and here high outliers, I think of like highly suspect outliers. Because I know low and high can kind of be confusing. But, and I'll kind of get into that later. But, okay, so if we have mild outliers, then that means that it's going to be between the lower inner fence and the lower outer fence, or it would be between the upper inner fence and the upper outer fence. And if we have extreme outliers, then it would just be, it could either be below the lower outer fence or above the upper outer fence. And I know there's a lot going on, and I'll try to break it down, but then I also have a neater version down here. So if I were to just kind of write out what the different parts of the box plot are, we have the hinges, which we have, like, this is the lower quartile, we have the median, and then we have the upper quartile here. The lower inner fence and the upper inner fence are these values here where the line kind of stops. So like here, to the first hinge or the lower quartile again is 25% of the data, and here is 75. And okay, yeah, so here's 25% of the data. From this hinge to here is another 25% of the data. Quartile 2 to quartile 3 is 25% of the data, and quartile 3 to the maximum value is another 25% data chunk. So here, if we're looking at the median, then here this would be like up to this point would be 50% of the data because we have 25%, 25%. But anyways, okay, so here we have these values here are the lower inner fence and upper inner fence. And then here we have the lower outer fence. So the dashed lines are the outer fence. So we have a lower outer fence and an upper outer fence. And so if we have a data point that's outside the outer fence, so here, then it's an extreme outlier. So that would be in this right-hand case here, if it's below the lower outer fence. And so this dotted line here is calculated by Q1 minus 3 times the interquartile range. And then this dotted line here is the upper outer fence, and that's calculated by Q3 plus 3 times the interquartile range. Excuse me. So if we have a suspect outlier or a mild outlier, that's going to be an outlier that's in between this dotted line here, dashed line, which is the lower outer fence, and then the lower inner fence. Okay, so so our goal is basically going back to here. We want to determine, we want to go through each of these numbers and see, are these, first of all, are they outliers? And if they're outliers, are they mild outliers or extreme outliers? So here, I first needed to calculate what the interquartile range is. So the interquartile range is going to be Q3 minus Q1. So, Q3 minus Q1. Q3 is 216.8 and Q1 is 196. So when you do that subtraction, you get 20.8. And then here, I'm also going to calculate the lower inner fence, the lower outer fence, the upper inner fence, the upper outer fence. And so here, this LF and UF is the same lower fence and outer fence that was referenced, let me see, in one of the earlier slides. So this is actually the lower inner fence and the upper inner fence. But I really am trying not, I don't want to confuse you either. So anyways, but if you recognize this formula, that's because we had, it was because task 1 used it. But anyways, so I calculated the fences by using the formulas. So we have for the, I first did this one, which is the lower inner fence, which is quartile 1 minus 1.5 times the interquartile range, which is 20.8. And so you get 164. And then the next one I did was quartile 1 minus 3 times the interquartile range. And so that you get 133.6. And then I also did these two formulas. So quartile 3 plus 1.5 times the interquartile range, you get 248. And then quartile 3 plus 3 times the interquartile range, you get 279.2. So then what I did was a much cleaner version of this, but with the information that we were given, and then the information we found out. So first, I just drew a box plot, and I wrote down the information that we were given. So we were given that 202.2 is the median. We were given 196 is quartile 1, 216.8 is the upper quartile, and then we calculated these are the fences that we calculated. So here 133.6 is the lower outer fence. 164.8 we calculated up here, and that is the lower inner fence. And then we have 248 that we calculated is the upper inner fence. And then we have 279.2, which is the upper outer fence. So after I had a clear picture of what that looked like, then I went back and looked at the different data points that we were given to determine whether they're outliers, and I plotted them. So the first one is 125 0.8, which is going to be somewhere out here. And so that's totally outside the outer fence out here. And so we would be in this situation up here. It's below this lower outer fence. So that is an extreme outlier or highly suspect outlier. The next value we were given was 188.1. And so that falls within the first, it falls within quartile, between quartile 1 and quartile 2. So that's not an outlier at all. That's, yeah. And then here we have 193.7. That's the same situation. So that's not an outlier. And then we have 221.3. That's not an outlier. And then we have 230.5. That's also not an outlier because it's falling between quartile 3 and I guess what you would consider the lower inner, or the upper inner fence, sorry. But then 250.2 is falling in between the upper outer fence and, or sorry, this is the upper outer fence and the upper inner fence. So this is considered a low and mild outlier. So you can see that it can kind of be a little counterintuitive when you're first learning this, that like this is considered a high outlier, even though it's like the lowest number in the data set, and this is considered a low outlier, even though it's the highest number in the data set. So I hope this helped. I know it can kind of be overwhelming, but my best piece of advice is when you're given a problem, write down the information that you're given so you don't get it confused with anything, and then to always draw pictures and to kind of plot what you know, and then to work from there, and then plot what you end up calculating, and then, you know, make your conclusions from that. And with that, I conclude this recitation, and I hope that it helped. Thanks for watching.